So let's welcome to all participants. Today we have Dr. Amit Chattopadhyay. We are honored to have you as a speaker for today's session. Amit is an interdisciplinary modeler and industrial explorer. Amit is a theoretical physicist at heart, but with bespoke applications in healthcare, sustainability, social sciences, and material science. Currently head of business analytics at the National College of Ireland. Amit continues to bridge the gap between physics, applied mathematics, and artificial intelligence to solve real world problems affecting human lives. His academic and professional background is very sound. He has done his PhD in theoretical physics from the Indian Association for the Cultivation of Science in 2011, followed by the first non-European Marie Curie Fellowship in Physics and an Alexander von Humboldt Fellowship. Global footprint with research and teaching leadership roles in the UK, Germany, Italy, Ireland, and India. This includes tenures at Aston University, University of Edinburgh, the University of Delhi. He is the present Vice President of the Irish Institute of Mathematics. 82 peer-reviewed publications, editorial board members of the Nature and Frontier groups, over £10 million research grant income. His research interests particularly specializes in repurposing quantitative methods from statistical physics, nonlinear dynamics, QFT, and AI to address real-world challenges in healthcare analytics, sustainability and engineering, development economics, material science, and many more. So I request Dr. Chattopadhyay to start his lecture. Thank you very much.
Thank you. Thank you, Kshitha. Thanks to everybody for the invitation, and I'll now share the entire screen because I think that's easier. And I'll switch myself off from the view now, just so that there's no flutter with the internet. Can you see the presentation now?
Yes.
Yes, yes, sir.
Yes, sir.
Okay, fine. Okay, fine. Well, first of all, thank you very much. It is an absolute pleasure to be speaking in front of you for the second time. And this is quite a 5 years gap now after the COVID. And thanks to Kishorda, thanks to Abhijitda for being in touch. Now, what I would say is, well, just minor correction in the details that Kishorda presented. My PhD, I'm a lot older than what he mentioned. My PhD was in 2001, but that's the only correction. The point is, we have had fantastic lectures over the past few years. Now, I just wanted to get started with a bit of an epilogue. The reason being, um, well, what exactly have we seen? And I was actually flabbergasted with the quality of presentations because it was live, impromptu to a certain extent, and very, very interactive. So this, I think, is a wonderful way of engaging students, engaging researchers, early careers, senior, whatever level of seniority they may be at. And this is exciting. So what we have had are excellent expositions of data and statistics. I'm not taking any particular names. So that's how I think we got started. And then starting from the basic builds to the more advanced mathematical applications, followed eventually by machine learning, to a certain extent, deep learning applications using Python as a base, and sort of scanning the horizon of different statistical, supervised, and unsupervised learning procedures across the domain. And then we also had applications in understanding the bacterial propagation, in drug repurposing, whatnot, lots of them. And what is very appealing to me at the personal level is all these different areas In fact, all the areas that have been spoken to are very close to my heart, close to my remit, and certainly of my interest. But, and if you would like to believe me, I requested for a later talk. There's a reason, because I just wanted to have an idea of how the flow proceeded. And what I've done is I've actually written the presentation yesterday and today. Kishoda knows that I was incorrectly assuming that my talk would be the day, would be tomorrow, which is why I thought I still had some gap. I didn't. So the presentation that I would be doing today would be fragmented into three sections, three different applications of digital healthcare using mathematical and AI modeling. And it would be more application oriented rather than coding driven. Of course, everything has at its heart, at its core, the coding infrastructures, things that you have learned. So what I'll try to do is I'll try to keep connecting you to the previous lectures, the previous builds that you have actually experienced, and then we will try and see how much of that affects real world implementation. By real world implementation, I mean real healthcare that touches everybody's life. And this is exactly what I do. So that's the focal point. So the focal point would be targeted applications in three different domains, three unconnected domains, I must say. And there's another epilogue, which is the fact that while Python is a very powerful programming language that you know and that you have been told, you have experienced yourself, it had somehow not such a happy precursor. It was called Perl. For those of you who are familiar with the language, you would know that it actually had almost the same level of acumen as that of Python. Somehow it just didn't lie. Also, the other point is, I come from the times, I'm an old timer, so I come from the times of Fortin 77, evolving into not Fortin 90, 95, C, C++, and all those. And they can still do all the jobs that we are doing. And in between, there was a programming infrastructure. So I'm mentioning this because a good part of the initial coding, the first part of the three-part lecture, was entirely using, if not entirely, to a good extent using MATLAB, and to a certain extent using Perl. Now, MATLAB, while it's not an open access software, it's certainly not open source. So it has to be paid for, but it has wonderful, powerful libraries, and that is what Python has successfully got motivated from and translated the MATLAB infrastructure into the Python infrastructure. And there's a huge bit of synergy. And this is something that I teach when I teach either programming language. The fact that with slight and minor input-output modifications, we can basically transfer MATLAB code into Python or the other way around. The reason being, both of them are by and large based in the C programming infrastructures. So, I mean, these are just going into a bit of logistics, but I thought this bit of historical connection makes sense, especially when we are learning a certain programming language and seeing how it can be applied in real world establishments. So, three areas, not infection, so hurt, drugs, and time permitting cancer. So three of the areas that I'm working on. So I am from the National College of Ireland, which is in Dublin, and these are my coordinates. So I mean, if you just type my first name with space NCA or even just the name on Google, I believe it, you should be able to find me. First, first work, cardiovascular risk modeling. And without any further ado, what I'll proceed straight on to is basically to try and connect with the jargon, and I will be very minimalist in terms of jargon usage. I'll just try to dig a bit deeper. CHD means coronary heart disease. CVD means cardiovascular death. Now, these are the terms that often you get to hear from your cardiologists, from your GPs, practically from everybody, even in the literature. So basically, what we are trying to understand is, what is the impact of coronary heart disease in cardiovascular deaths? So that's pretty much the question we are trying to understand. But slightly deeper than that, we are spanning, I mean, this study actually used data from 13 different countries, largely built on the World Health Organization, but also there were other data sources. I will show you that. And most of the results that I will show you in this part are for the UK, but at the end I'll show you results for 12 other European countries. We have also analyzed the American domain, and the results are remarkable. The results are remarkable. First and foremost, I just want to give you the understanding of why we engaged into this particular study, which was a PhD project of my second PhD student, who, based on this particular work, became an NHS National Health Service UK data analyst later. Um, it starts from the point, if today you have a heart disease, you go to your cardiologist. If you go to a cardiologist, the cardiologist basically does the risk assessment. So they go through the BMI and all those different indices, and eventually they tell you, okay, you are fine or you are not fine. If you are not fine, they will put you under some sort of a treatment regime or not. Important point. This risk scoring mechanism, if you are in India or if you are largely in Europe, the formula that's used is something called a Q risk. If you're in America, they largely stick to what is called the Framingham score line. Both are wrong. Wrong why? Because these are sorry, hugely linearized approximations of the data that they had, and these were still epidemiological data, not longitudinal data, hugely linearized. And essentially, it means today, when we go to a cardiologist and when we are given a medication, it's largely based on the wrong premise, and they know it. That's what we are trying to improve, at least in the UK side. So the discussions are ongoing following this work to integrate the findings with the real lives, the real NHS structure. So I'm a theoretical physicist. So the presentation will be looked at from the lens of a physicist. I'm not a biologist, so I will be apologizing to the more biologically perfect audience. My focus would largely be on the impact of lifestyle factors on coronary heart disease and eventually on cardiovascular death. That's what we will try to do. And we will focus on the bad factors affecting the heart. Some of them could even be good factors. Some of them are interconnected. The bads connected with other bads, the goods connected with the other goods, the bads that are connected with the goods. And it will be an artificially intelligent model focusing on the quintessential question, how many portions a day? So I am sure all of us get to hear this every day, probably in many different health forum, definitely 5 food portions a day, 5 fruits, vegetables, etc. Why 5? Why not 35? Why not 25? Why not 1? I leave this question at this hanging at the moment, and I will try and come to an answer. Probably you already have an answer. If not, I'll give this answer later. And eventually, we presented an algorithm that can actually do real personalized data analysis and predict what is the real heart attack risk of a certain individual. That's what we are doing here. This is just a little bit of a backdrop. I'll pass through this particular phase quite fast. So it basically goes to say that the Heart UK Foundation, which is sort of the government portal presenting you the stats for the UK, it's pretty much telling you that every 12 minutes there's somebody with a heart attack, and there are scores and loads of people being affected. This is the UK side. UK side is probably even worse. And the surprising thing is, some of the popular conventions, and this is something that I will show you in a second, some of the popular conventions like having greasy food, cheese, for example, in our case, sweets, Schomdish. So the fact is, there's a popular misconception about the fact that cheesy or cheese consumption is counterproductive to cardiovascular health. You will be surprised when I show you the stats just in a few more seconds that the countries producing and consuming the maximum volume of cheese, countries like Italy, countries like Spain, Greece, etc., are the ones with the least heart attacks. What does that tell us? It tells us it's a multi-dimensional structure, not reliant or dependent on one factor. And one factor, the fact of, for example, the volume of cheese consumption, is a function potentially of the other different factors and something that cannot be predicted or ascertained using linearized statistics. Okay, so that's the backdrop. What happens? This is what happens. So there are two reasons. One is age, and the other is natural buildup and unnatural buildup. Unnatural buildup because of the lifestyle that we adopt to. So what is it? So imagine that you have a heart, you have your artery, and the artery has certain inner linings. The inner linings basically get affected by two different types of cholesterols. One is called an LDL, low density lipoproteins, the other is the high density lipoproteins. in sort of crude terms, the HDL is a good thing, LDL is a bad thing, because LDL can be washed out and HDL can actually reduce the effective concentration of LDL. It's like a washer, if you like. But basically, what happens with time is, as we grow older, the elasticity of the ventricles, of the arteries, the elasticities go down. They become a lot harder, and hence the propensity of forcing out these plaque, that means the deposit cholesterol, reduces. And with time it grows. Essentially, it simply means that the effective surface area of blood conduction goes down. And at some point, completely chokes. When it completely chokes, it bursts at a certain point, and this is the situation where we have some sort of a thrombosis. It could be a heart attack, it could be cerebral, but it's basically because of two jargonic words. One is called atherosclerosis, one is called arteriosclerosis. I won't go into the biological details, but basically take it like it is clogging the arteries and the veins. So that's pretty much what's happening here. And what we are after is trying and finding, quantify which are the more responsible factors responsible for the growth, what is the rate of growth, and which are the most important factors in order of ranking. So that's the journey that we are engaging onto. So the bad factors, what we call the predators, we will abbreviate that as B, are things like the high cholesterol, alcohol. Just bear in mind, these are all interconnected. Somebody with alcoholism or a regular consumption of alcohol by default has a higher cholesterol than somebody who doesn't, with roughly the same sort of BMI and other stats. Same with smoking and hypertensions. There are two types: systolic and diastolic blood pressures. Food habits, I mentioned cholesterol, and they engage in connecting with triglycerides, cheese, as I just mentioned. The ones in black are the ones which are also very, very important, but unfortunately for those which we didn't have any reliable data for. So ours is in a way truncated study, and this is what we are trying to go on and work together with the National Health Service in the UK to make it more system facing, more direct, and more application oriented to integrate the other factors, because the mathematical, the algorithmic architecture that we have designed, it can accommodate any number of factors for which you have data. So these are the ones that we haven't incorporated: genetic impact, circadian rhythm, mental health, and there are others. I'm just pointing to the main ones. Good habits, fruits and cereals, vegetables. And there are loads that we couldn't integrate with. We know that exercising helps, we know that healthy dieting helps, we know that sleep helps, we know that controlled medication, aspirin to be more specific, helps. And this is sort of a precursor to the next part of the talk that I will give today: drug repurposing. I would be focusing on not just aspirin, but just basically it would be something which would come often in the context of repurposing. We will come to when it comes to. But basically, it's a concoction of the good factors and the bad factors, and I've said that the bad factors are interconnected. So basically, you can say that blood pressure is a function of smoking, alcohol, and high cholesterol, whereas alcohol itself is a function of cholesterol and smoking. It's a complicated mathematical structure with some many to one map, which is very, very difficult to decipher. So, in other words, we are in a multi-dimensional world where even when we have been given the data, there are hidden connections between the individual profiles, hidden features as we call them. These features need to be properly assessed, their interconnections evaluated, and only then will we be able to ascertain a proper health risk and make viable predictions. This is the journey that we are engaging onto. So, this is something that I've just said: why 5 portions, not 4 or 7? If I simply increase the good food habit consumptions and reduce the B, does this mean that I will never have a heart attack? You know that the answer is no. That doesn't mean that. Can I, for example, and this is the last question in this particular phase of the talk that I'll go on to, so, for example, increase a bit of fruit consumption, increase a bit of vegetables, because my cardiologist told me that these are good things, and I am a bit reluctant to exercising, and simultaneously I also want to go up a bit on alcohol over the weekends. What is the revised risk of a heart attack for me at the start of Monday or Tuesday? So that's the sort of question that you can answer with this sort of a study. In other words, can a mathematical AI-based model predict heart attack? So this is raw stats, as I see. No machine learning, nothing. This is real stats. Just look at what we are seeing here. So we have data from 1990 to 2013. So this was the data line that we used. And as you can see, up until every plot, I mean, this is the alcohol consumption, the first one where my cursor is moving. Then on the right, you have the cheese consumption. Then you have the smoking habits. Then you have the systolic blood pressure. And at the bottom, too, you have the good foods, the cereals, and the fruit and veg. Now, look what's happening here. In the UK, alcohol consumption hit a peak at around 2002-3, and thereafter it started a steep decline. Whereas the cheese consumption is largely on a linear progression path, smoking is on a linear decreasing path, blood pressure is on a slightly non-linear but still on a decreasing slope. The good habits have gone up. That means people are eating more cereals, people are eating more fruits and veg, and all those things. So basically, like what is said at the start, it's a concocted mixture. Now, this is something which is the starting point of our analysis. Now, we have, like what is said, this is not something that I will focus a lot of time on, but basically we have to analyze data for all these different countries and have just published for the UK sector only. The plan is to publish for the other sectors in time. And surprisingly enough, the Mediterranean bloc, which is the main cheese producer, is the one that has or sees the least amount of heart attacks, both for the males and the females. And please remember that the risk probability for the male female for each of the individual sector I will show you now are different and culminating into them having different heart attack probabilities. So a man is more likely to have a heart attack irrespective of the country concerned, but likely is how likely depends on the country we are talking about and depends on the habits. So these are the data repositories that we have used. These are all open sourced. Anybody can go and access those. You really don't need much of a subscription. It's only the FAO stats where I think you just have to open an account, and otherwise you can just access it anywhere. We have used data up until about 2013, but the data is now updated. We can actually update the records, and that's under the new paper that we are writing at the moment with the updated stats. This is the death rate as a combination of all these different good and the bad factors that I have shown you, and this is for the UK. Look what's happening here, and look what is this year 1992. It's marked for a certain reason. First of all, before 1992, starting 1970, there was a slow linear trend of increase in death rate, and there was a fast decay since 1992. The green plot is for the females, the yellow plot is for the males. As you can see, the males have a higher risk, but still it's on the decreasing slope. The question is, what happened in 1992? 1992 is the year when a statin was made publicly available to the National Health Service. That means statin was being made accessible to the common public. It had a dramatic impact on the death rate because dramatically the the CVD cardiovascular deaths reduced for obvious reasons because actually these are the medications that can clean the plaque. The important point here is, I have repeated it a few times, and this is the final time probably I say this, but basically, the trends, surprisingly, and without a reason that I can decipher or explain, both the growing and the decaying trends are by and large linear. And that made up a job extremely good. The reason is that this is the sectorial part where this stands in 1992. It's not exactly 1990, but thereafter you have the decrease, and this is the part that we are more interested in, both for the males and the females. Now here is again. This is a reminder, and these are the stats for the different countries. So if you look at the coronary death rates for all these different countries that we have suggested, the males and the females have different numbers, but very importantly, please note the negative value of the gradient. It means all of them, irrespective of the country, they had a decreasing death rate ever since statin got introduced into their health system. For UK, it was 1992. For Denmark, Finland, etc., these were different times. But once it was implemented, it was a fast decreasing, surprisingly though, linear rate. We did not have female data for them, but we had male data. These are the different data crunched statistics. Alcohol consumption rate, you would see that some of the countries still show positive alcohol consumption, essentially meaning it's still even though slightly but on the rise. Smoking. Negative means decreasing, positive means increasing. These are the gradient values, linearly fitted, least square fitted gradient values. Okay. Now, I use the word least square fitted, so obviously this is not probabilistic because I haven't done any machine deep learning or even proper statistical modeling yet. This is what we will do now. So this is the structure. So the literature survey leading connected to biology and mathematical model, acquires the data source that I've just shown you, synthesize the data, essentially meaning clean the data and make it ready for your learning, statistical learning, and then first analyze through linear statistics. Surprisingly, our statistics was linear, both in terms of the death rate and in terms of the different good and the bad lifestyle factors. We will visualize the data and we will take different linear and non-linear regimes of visualization, and eventually we will do some sort of a regression prediction. But regression, I did not mean linear, non-linear regression predictions. Eventually, that would actually connect with real life. So the techniques that we have used are the following, and here I will take a slight bit of a detour, which will come in a second. I know that you have been introduced to machine basic Python programming. You have been used to using NumPy. You know how to use sklearn, for example, and by and large, and you also know how to use the matplotlib. So I will combine these three coordinates just to give you sort of a real life feel of what the PCA architecture is, and then we will proceed to say, well, PCA is not good enough because it's linear. So what changes in making it non-linear and how the non-linear part connects closer to the data. So I'll take a very bad, crude example of a simple 3 by 3 matrix as the starting data point, and I will hack this within the PCA architecture, and we will see what comes out of that. And then we will go on to some of the non-linear kernels, so non-linear or properly called kernel PCA. And we have used the different other forms of in learning. One is called Neuroscale, the other is called GTM, topographic mapping. The last one is called Gaussian process latent variable models. Basically, you superpose a lot of different Gaussians to extract the hidden feature architecture. Each of them is mathematically independent. Each has its own advantage and disadvantage. We won't have the time to go into all of them. So we will touch base on the one that probably is doable within this time frame, and then we will sort of verbally try and understand a little bit of why the other methods were implemented and what change they made, and eventually we'll crunch the numbers using the different architectures. And obviously, statistical modeling, be it machine learning, deep learning, be it generative mapping, any sort of an architecture, we need to do the validation, and that's something that I will show you as well. So we'll see how the validation mechanism actually worked. Now, this I won't spend a lot of time. Cars of higher dimensionality. Now, we don't have really high dimensions here. The reason being we are focusing largely on correlated 5 bad factors and 2 good factors. But if we had real access to all the good and all the bad factors, it would be genuinely high dimensional, because then the total number of affecting factors would be more than 30. And then that becomes a high dimensional regime and high dimensional analysis. High dimensional means it's open, it's more volatile, so the predictions are more likely to be false. So you generate a lot of false positives, false negatives. You need to be, you need to have the right sort of a statistical architecture to deal with that. That's not a main problem here. So the techniques that we are largely using on the left-hand side are the supervised learning, on the right-hand side are the unsupervised learning architectures. Just to remind ourselves, supervised learning would mean you know the features and you know the target. So you're connecting features with the target, which doesn't mean that each feature connects to each target. It might be many features connecting to one target, or sometimes multiple targets associated with a single feature. But the important point is you know the features, you know the targets. Unsupervised would be one of the sides is trailing off. So basically, for example, like a clustering. So if you're doing a clustering mechanism, then that's unsupervised learning. That means you have the data and you do not exactly know what are the important features. So you want to find out what are the important features by doing something. That something would be within the architecture of clustering, and there are other methods. Now, this is the very popular way of defining. I'm not pretending that this is something that I have innovated myself. I pretty much copied the statements from the very popular textbook by Steve Bishop on neural networks. And this is how the PCA is defined. It's a fantastic book that I heartily recommend to anybody interested in machine learning. So, especially on the mathematical perspective. So this is what I have written down, and what I will dumb this down onto now is to take a simple example and run us through the simple example to see first how you can take a pen and paper, do the calculations, and then we will translate that pen and paper into a Python step-by-step architecture to see how the whole mechanism works, what we see, how it works, and then we will come back to the main topic. Okay? By the way, if you have any questions at any point in time, please don't put it on the chat box because I won't be able to see it. Just speak out. Okay. So this is what I was writing actually today itself. So imagine you have some data which I call the Z matrix. Okay, and it's a 3 by 3 matrix. I have taken 3 by 3 because I just wanted to do some handwritten calculations that I can show and share with you. So what is the mechanism? What is PCA? So PCA is principal component analysis. What does it do? Well, given the data, it's a 3 by 3. As an example, it could be n by n. Potentially, it could be n by p. N being the number of data points, p could be the number of features. It could be basically a non-square matrix as well. So, okay, let's start with a simple situation, 3 by 3. So, essentially, the first step to that is you take the means. Just recall what we do for the Z score. What is Z score? Given the data called X, we subtract the data from the mean and divide it by the standard deviation. Why do we do that? Because that then means that the probability density function or the histogram of the Z variable, PDF of Z, would actually be centered at 0 for the mean and 1 for the standard deviation. So the spread is 1. So this is something equivalent. So basically, you go column by column. So take the first column, 1, 4, 7, and the mean of the first column is 4. The mean of the second column again is 4, and that of the third column is 1. You just add up 1, add 1, add 1, 3 divided by 3. That's 1. Okay. So the means of each of the column, and then you get the mean normalized score, something equivalent to the Z score. So you subtract the mean for each column from the entry of that particular column. So the mean for the first column was 4, 1 minus 4, 4 minus 4, 7 minus 4. Back for the third column was 1, so you take 1 minus 1, 1 minus 1, 1 minus 1. And this is what you get. The next step is you have to take a covariance of the mean, or we call the centered matrix. So the centered matrix suitably normalized against the number of entries. So it's a 3 by 3, its dimensionality is 3. So 1/3 of the mean normalized matrix that we call Z1 transpose times Z1. And that gives you this. Okay. Then you calculate the eigenvalues of this covariance matrix. The eigenvalues for this particular example that I have taken turn out one is about 13, the other is close to 1.92, and the other is absolutely 0. And the two leading eigenvectors that you can calculate are following: v1 and v2. And the feature vector, please note, we started with 3 vectors, right? 3 columns are 3 vectors. And now we have reduced them to the level of 2 vectors. The point that I'm trying to make is instead of 3 columns, you could have 1,000 columns, 1,000,000 columns. PCA architecture is basically telling you which of the linearly combined columns will give you the best mapping from the data space to the projection space. That's what PCA does for you. And essentially, the quality of projection is 93.4% of the data is encapsulated within the first feature vector v1 and about 6.6% in the second feature vector. This is an exceptional example where nothing is contributed by the third. That simply is because the third eigenvalue is equal to 0. Okay, now what I would rather like to share is how do you replicate the step-by-step mechanism when you are dealing with a Python. So let's just open, and I will cheat a little bit here.
Sir, extremely sorry to interrupt. I think there are some
From
questions from some of the participants in the chat
oh,
box.
that is a very difficult thing because
Yes,
I
yes, sir.
won't be able to add box. Okay, let me see. Controlled. Okay, you show the control medication, medicines is okay. No, I didn't mean control medication. I meant a medication suggested by the doctor. So basically, um, the doctors, when they suggest you medication, they use a certain score line, and my point was the score line, the risk scoring mechanism, is hugely restricted, and the medical scientists are informed about that. In the two countries, like for example in India or Europe, we use a certain score line called Q risk, which is a linear architecture. In the US, they largely use a Framingham score line, which also is a linear architecture, and this being an inherently nonlinear mechanism, superposing something with a linear structure is wrong, and the doctors know that. And unfortunately, the medications based on that are also very questionable. That's what I wanted to say here. Um, no, I think, Debom, I'm just trying to answer your question now. Looking at data visualization using lower dimensions, no. Absolutely not. Dimensional reduction essentially means, and there are many different techniques. The one that I will have just gone a little bit through is PCA, which is the simplest and hence the most inaccurate, to be precise, because it's a linear mechanism. It's a linear superposition of vectors, and it's assuming that the data are linearly correlated, which mostly it is not. Certainly, in most real life scenarios, that it is not linearly correlated. But basically, the architecture, the understanding is whatever method you might be using, you have a lot of dimensions. That means a lot of different variables, let's say, and you want to understand what combination of these variables can actually be done such that you can focus on two suitably combined, linearly combined set of variables. That's the PCA architecture. There are different mechanisms which can actually give you rankings of individual variables. So the point here is you have higher dimension refers to all the variables, and lower dimension refers to essentially combining all these different variables into two leading vectorial forms, and the contributions would be the respective proportional contributions would be the respective eigenvalues. Is that clear now, or is it unclear?
Yes, you carry on.
Okay, right. So now what I will try to quickly lead you through, I was on Google Colab and cheating. So cheating in the sense, I'll copy this example from Google Colab that I normally use as my experimental toolbox. And I hope it works actually. Okay, so I'll quickly lead you through what I have just written down. So I have taken the same Z matrix that I have just used, 1, 2, 1, 4, 2, 1, 7, 8, 1. That's the one that I have just used. Here we go. So this is the matrix, the Z matrix. So first of all, define the matrix as an array, and the way you do that in Python would be to use numpy np dot array, first brackets, then third brackets, and each third bracket encapsulating the rows within further third brackets, just like what I have done. Or alternatively, you could actually take each one of these. For example, this one you can define as column 1 or row 1, this one as row 2, etc. separately, and you can simply write column 1, comma, column 2, comma, column 2. That also is perfectly fine. But the first step is you want to do to calculate the mean of each column. So the mean of 1 plus 4 plus 7 divided by 3, whatever it is, 4, 2 plus 2 plus 8 divided by 3, 1 plus 1 plus 1 divided by 3. So this is done in the next step. So again, you have to put, when you're using NumPy, you know that by now, you have to put np dot pretty much whatever you were trying to do. And by and large, Python, Perl, MATLAB, etc., they operate on your common sense argument. Mean is mean. So np dot mean, bracket Z, axis equal to 0 is basically identifying that you're going column by column. Okay. And now the next step would be subtracting the mean from the data. So the mean of the first column would be subtracted from each entry of the first column. Similarly, the mean of the second column would be subtracted from each entry of the second column. Okay. So that's the second step. And if I was doing just that, we can actually do just that. I'm just copying this bit. So if you, this is in Google Colab, if you just take that bit and if you run this thing and suspect about my internet connection, okay, just done that. So it has given us the answer. Here is the answer after the subtraction. Okay. Now that we have done the subtraction, let's just proceed into the next step. We calculate the covariance matrix. Okay. Covariance matrix is the normalized 1 by n. N is 3. You can pretty much brutally write here 3. And this is Z1 transpose multiplying the Z1 matrix. Okay. So this is the next step. So we can now go back here. We add this particular bit, run it again. And now we have got the covariance matrix 660, 680, 000, just like what you saw me doing here, this guy there, sigma. Now we have to calculate the eigenvalues. So to calculate the eigenvalues, you can use the, again, you use the inbuilt structure. So the reason I'm spending some time on this is I will be using similar architectures across the board for the other two applications. Okay, so now I'm calculating the eigenvalues and the eigenvectors, and you can use this particular subroutine or inbuilt, well, you can call it a subroutine or you can call it a library, lin for linear, ALG for algebra, linear algebra subroutine. It's a bit like, for those of you who are familiar with Linux infrastructure, be it Fortran or C, you are familiar with using LAPACK. So it's the LAPACK version for Python. And all you do is literally you just copy the covariance matrix as the argument. And here what we are doing is we are identifying the one to the first. Typically, we are interested in the top two eigenvalues. So that's what we are identifying now. And we calculate the eigenvalues, and then we calculate the corresponding eigenvectors. I will do this now and print them out. Okay, so eigenvalues, like what we have just seen, are the following, and they have to be normalized. Okay, 13.08 and 0.917 is 0.92. If you look, this is what I had here, 13.08 and approximately 0.92. And then you have the eigenvectors, which are here. So the first two dominating eigenvectors, which we call the feature vector space, this is the column 1, and this is the column 2 here. Now, is this the only way that, I mean, if you have to use Python, would you have to undertake this particular mechanism step by step every other time that you have to do? Not really. So what you can simply do is you could actually use the inbuilt, and I will show that to you now as well. And this has a certain advantage, although I recommend for the starters that you should try and dirty your hands at least once. Should see how it actually essentially works. Okay, so I am now copying pasting another code. Now I would be using the sklearn library, and I'm importing PCA, which is already, so all the steps that I have just shown to you, you see I have highlighted and it is telling you what it is inside. Okay, so it has all the infrastructures, the step-by-step infrastructures inbuilt under something called PCA, and essentially all you need to do after that is you define your input data, which is Z for me, and then you just basically say how many components you want. I have written 2. You can write 3 if you wanted to, 4 if you wanted to, given the data size. And then what you say is you just use this fit transform. And if you just ask, you will precisely get the output straight away. Now, there is something that we may need to understand here. Why did I not recommend us using this? What is the advantage or disadvantage of using this brutal approach? The advantage is it's short, it's precise, it's direct. The disadvantage is very often we use methods copying pasting from somebody else's code without knowing what's going on inside. The problem with that is each algorithm has its own advantage and disadvantage. So you will definitely get a result. Whether that result makes any sense in the context of the data that you are studying is something that you only have to understand And you understand that only when you know the data structure inside, for which sometimes a step-by-step approach is very good. But this approach has the added bit, and this is what I will show you in the next slide. The added bit is I can simply tweak this code, inherent code that I have written, only that I will change PCA to nonlinear PCA and it kernel PCA, sorry, and it will immediately give me the answer for the nonlinear description. Let's see how it actually looks like. So what is it? What is it that is missing? What is missing is I'm assuming the data and all its variables are linearly connected. So, for example, if I double the my alcoholic consumption, my heart attack rate would be doubled. If I double my smoking, then again my heart attack rate gets doubled. If I double both of them, then my heart attack rate becomes probability becomes quadruple. Now that's just wrong. Okay, and to address that, what you need to do is that means you were saying that you know that the data is potentially nonlinear in its infrastructure. So then what you do is you just translate your original data set X into, you map the data into something called a kernel function. Okay, there's this popular mathematical thing called kernel trick. For those of you who are into machine learning, you know that we use the same thing in SVR and SVM, support vector machines. So basically, all you do is you go back to your. I'm just taking a little bit of. You go back to this data set, original data set, and basically what you are trying to find is you calculate. You take any two column, let's say the first column and the second column, 1 minus 2 squared, 4 minus 2 squared, 7 minus 8 squared, multiplied by a very small fit function gamma, which is this. We have taken a very small value for gamma, which is normally what you take. I'll show you that. And then essentially you calculate, you translate your X data into what we call into this Kij data set, which is called the kernel matrix. And whatever you did, calculated the covariance, etc., for the real data, you do the same now using the kernel matrix. So X now becomes K, and everything else remains unchanged. So basically, this approach generates again eigenvalues and eigenvectors, but these are eigenvectors which can decrypt the hidden nonlinear patterns within the structure. Okay. Now, if you are not convinced, and there is no reason for you to be convinced, let's try and just do that. Let's to see what happens when we do this using the same super simple problem, but now using kernel PCA. So let's just go back a step. This is the same Z matrix. This is my data set, Z. Okay. Instead of kernel PCA, I'm using the radial basis function that e to the minus of gamma xi minus xj squared. So all I'm doing is, instead of the PCA, I'm doing something called kernel PCA, again called from sklearn. Okay, you are calling instead of PCA kernel PCA. That's the only change. Otherwise, you just copy paste the same command, and when you hit the run code, you see the eigenvectors that are generated and the eigenvalues, they're substantially different in terms of numbers than what you previously have seen. So that is remarkably different, and that then essentially tells you that this is, first of all, look that this is actually centerized. If you add up all the numbers, you will get a 0 from either side. Okay, so that means it's the mean is genuinely at the center, and its spread, when calculated, can actually be made to be a spread, means the standard deviation could actually be made to be equal to 1. The point is, these are not the main things. The main thing is it spits out different numbers, which is a reflection of the hidden nonlinearity that simple PCA cannot track. So we use PCA just for the clarification bit, but for the real analysis, we are using the nonlinear methods that I will show you now. Let me quickly have a look. Any other
Importing
questions?
nonlinearity result differs drastically, right?
Yes, yes,
Ah,
yes.
that's the problem.
Absolutely. Absolutely. And this is the whole heart. You have got it right, Kishore. I mean, this is the whole point. because I'll come to this in a second. Because when I'll show you the result. We are super lucky that in the particular data set that we were studying, the linearity and the non-linearity were not too different for this cardiovascular set. When I go on to the next example, they will be dramatically different. This is just a property of the data.
Then
In our case, we were lucky.
how do you connect these eigenvectors and eigenvalues with the real interpretation of the problem?
Oh, okay. It's slightly long drawn, but basically what it means is, just imagine that I'll take a super simple example. So let's say you have three numbers, 1, 2, and 3, whatever they mean, and you have got 1, 2, and 3. So you've got 2, 4, and 6 in an opposing space, in a connected space. So basically, you know the connection between the first set and the second. It is the multiplier by 2. Okay, just imagine that it's not multiplied by 2. Instead of 1, 2, and 3, you have 1 square, 2 square, and 3 square. Now, that, if you have the data like 1 square, 2 square, 3 square, or 1 cube, 2 cube, 3 cubed, that, if you are doing a linear superposition of 1, 2, 3 to predict whatever might be happening on the other side, it will completely fall flat. So that is what this thing will do. So this will actually approximate. It's largely based on the idea of central limit theorem, and the kernel function that I showed you, the RBF function that I showed you, the radial basis function, it is a Gaussian function. So basically, it is saying that you go on and add corrections to the Gaussian functions up until the point which it actually maps the PDF, the probability density of the real data set, correctly onto the other data set.
Okay, okay.
Does it
Understood.
make sense?
Understood.
Okay. So basically, that's what we have done. So this is the mathematics that we have just gone through, and here we come to the results. The PCA, I'll show you the results straight away, and you will see it's dramatically different. So the different colors are showing you here. We are talking about the 4 negative, that means the 4 bad factors, and the 2 good factors. Negatives are the things like alcohol, smoking, etc. And they're comparable. So you cannot, using PCA, you cannot actually decide which one is more important than the other one. Straight away, you see where we are going wrong. Again, PCA, the previous one was for the males, UK males, and this is for the UK females. You can't decipher. Now you look at PCA visualization, when you're incorporating more factors, it doesn't actually discriminate in between the two. I won't spend a lot of time. This is a bit more mathematical than for anybody who is interested. Please, I suggest have a look at this particular paper, which is here. So this is the paper that we produced in connection. So if you just type my name and CHD risk minimization, you will get it. Okay. So we have the details, all the details are there. So basically this part is actually checking and verifying how trustworthy all these calculations are. As one can show that TK max would essentially, these are the results for the T values. Just look at the numbers. PCA generates this T value, which is close to 1. So does the other forms of dimensional reduction, neuroscale, topographic mapping, and latent variable mapping. So all of them are around zero point 0.9 and above. And when I'll later show you the values for the MRD, mean relative rank, that those values need to be on the smaller side. So they're not a lot different. So we are very lucky, and we are lucky because, if you remember, the data already showed them to be largely linearly generated. We have no reasons to understand and explain why, but it's just the real data that I showed you at the start. That's the reason, I believe, for which PCA to a certain extent is working in this particular example. Not everywhere. Very definitely not. Now, these are the different results. Remember, the question is, when you map y against x, it's not a problem, you know how to say it. But if y depends on x and z, when both x and z are simultaneously changing, you know, to understand y, you have to look at a surface, not at a line. And when you have more than that variable, you have a hypersurface. So basically, you can't see anything. So this is what is happening. You have multiple factors varying at the same time. And the core understanding is, this is what the mechanisms, our methodology, combining all these different architectures, predict that for the males, for UK, Blood pressure is the most important factor, followed by smoking, cheese, and then alcohol. So apparently, alcohol consumption is supposed to be the least of the marauders. So alcohol has the least effect in terms of heart attacks. But please do not read this as me suggesting that alcohol consumption is a very good habit. Absolutely not. My point here is quite the other way around. I'm saying comparatively, all these factors are interconnected. So blood pressure increases when you have alcohols and etc., which is the reason that blood pressure independently stands out as the worst inflictor for the males, whereas for the females, smoking turns out to be the worst. Okay, so take all these things with a bit of a caution because this is just based on data modeling. It is not what we call process modeling. It is not the biology inbuilt into the process. And these are the non-linearly regressed architectures. And I'll show you in a second in a simple plot what this means. So basically, it profiles that this is what we are proposing that the doctors should be using now, that they just ask for the number of units of alcohol, smoking, cheese, etc., that the patient has consumed over the last certain amount of time, put all these numbers in. SBP will be coming out as the risk score measure, both for the males and for the females. Now, what and exactly how that matters is, so we have done these things for all the different countries. And one thing that I just wanted to draw your attention to is the fact that this relative ranking dramatically changes for the countries, but they largely remain sector driven. So all these countries within the same sector have the same sort of a behavior, whereas for Scandinavian countries, they have a different sort of ranking. But within the Scandinavian sector, Denmark or Norway, they're not largely different from each other in terms of the cardiovascular attacks and their affecting factors. So this is a representative plot that I like very much. So the first row essentially means that you have decided to increase your good food consumptions. C stands for cereals, FB for fruit vegetables. So you've gone up 10% on cereals, 10% on fruit vegetables, and you see that when you have not done anything with alcohol, smoking, or cheese, your blood pressure drops by about 3%. Now, you have increased fruit vegetables by 20% and kept the other ones the same. It has gone down by 9%. Do you folks see that a doubling up in the fruit vegetable consumption generates the trebling effect on the blood pressure, so it's non-linear, right? Now what we are doing is, let's have a look at this particular line, the line here. So this line here is very interesting. You have increased your fruit cereal consumption by 10%. Fruit consumption remains where it was, nothing, no change. Alcohol, smoking, no change. But you have decided to go to McDonald's and eat a lot of food. Okay? So what it tells you is, if your cheese consumption increase is within about 2%, and you have simultaneously gone up 10% on your cereal consumption, your blood pressure, that means your heart attack risk, largely stays unaffected. That's what it says. So basically, what it means is the doctor can actually tell you precisely, depending on your lifestyle coordinates, what heart attack risk you stand. That's the purpose of this particular structure, and we're planning to design it like an app. And this is a summary that in the post-statin era, that was 1992 for the UK, coronary deaths have dramatically reduced. We have seen that the lifestyle habits are regional, ethnicity, and gender dependent. Now, this part we know we haven't probed yet, ethnicity. We have probed it for the region part. And we haven't done anything with specifically with region and gender combined, but we have seen that the males and the females, that means the gender, are differently or differentially affected by heart attacks. Okay, this is the name of MUM is the name that I have given. Mend your mind. So basically, it's the name of the algorithm, the one that I have just shown you, which is supposed to do all of that. And this is the team that we work towards. And now at the moment, what we are doing is we are actually working on the longitudinal progression of the data, and we are trying to analyze what and how much of the epidemiological prediction holds true for the longitudinal domain. Okay, so that's where I will, well, it's not me, but it's somebody else. So it's a team across the domain, and we have people from the different domains. Professor Gautam Ghosh, apart from being the vice chancellor of certain multiple universities, he is the top vaccinologist, one of the best in the country. He was, I think, the CEO of Panacea. Shubha is in Bangalore, a frontline medic who also has a PhD in machine learning. So we are all working together, and all the other names. Dr. Bellari is one of the top diabetes consultants in the Midlands in the UK. Matan and she were formerly students, and they are now professionals. So these are the lead papers, and there are others that are coming up. So just to stop for a few seconds, is there any pending question that you want to ask?
Yes, I have a question that you showed your machine learning predictions, right? So how much it is realistic? I mean, have you checked it with a real life scenario?
Yes. So the way we did the entire thing is, I'll give you more details in the other talks because I have got the slides showing you that. But basically, the architecture that I always follow is the following. So imagine that you have your certain data set, and I always use about, and I keep sampling around 80% of the data set for training the data, and I then use the remaining 20% for the prediction. Now, which 80%? This 80% has to be randomized. It's not just the top half of the data, and then you just remain, because then that's a biased data. So we create many different stochastic ensembles of this 80% and then the remaining 20%. So for each 80%, we do the training, and the remaining 20%, we get the predictions, the numbers. We randomize the data again. So the new 80% is another new 80%. We repeat the whole process and then make the predictions based on the 20%. So the results that I was showing you were the prediction validated results, and the prediction level are close to 99% accurate. Those are the t values that I have shown you.
Good. And second question is, did anybody explore India's data? I mean, if so, what is the result?
I don't think anybody did, honestly. But, and the main reason for that is, see, the point is, when you go to the World WHO website, potentially all countries have their data, right? But data means what? I mean, what volume of data do we have access to? The problem with and this is also a problem with the UK, but thankfully UK has an inbuilt detailed data structure. It's a very complicated mechanism, but there is a repository, honest data repository, that if you manage to jump through a lot of hoops, you would be able to access. Same with the US. Practically nothing for Europe, and almost definitely nothing for India.
Yes, that's the real
So
problem. There is no data repositories.
there is no data repository. I have done a completely different prediction structure. This is a completely different paper that I will not talk about today, but I'll just refer here. It's the dengue prediction. Okay, so we got anonymous 100 patients data, and the using machine learning, what we were trying to do is, okay, what happens when somebody has an infection? Well, the person, you first speak with your doctor. The doctor thinks it's a problem, so you go to the hospital. Now, when you go to the hospital, at the point of entrance, you're evaluated on three risk scores: low risk, mid risk, high risk. If you are low risk, you are asked to go back home with probably some medications. If it is mid risk, you are kept in the hospital for a certain length of time for evaluations. And if you're high risk, you're probably put in ICU, some such thing, right? So what we did was we got access, personally collected data for 100 patients, and we used machine learning. So bear in mind, it's sparse data. 100 data points is nothing, but we were still extremely successful in almost accurately predicting more than 85% of the hospital admissions, which was better in terms of prediction than a panel of 10 consultants taken together for the same hospital. And this is the problem. So this was done because we knew somebody who was painstakingly collecting all the data. But if I ask what is about the data, I mean, forget it, the whole of India. But if I say, can we have data for all of Calcutta or all of Bangalore? The answer is absolutely no, because there is nothing like that.
Okay.
Okay, so the first part consciously was longer because I wanted to lay down the backbones of the structure. Now I will move a bit faster, And the focus now, henceforth, instead of the infrastructure that hopefully is a bit clearer. So we're using for dimensional reduction, PCA is not what we are using, but I nevertheless used PCA to explain how the mechanism works. We are using kernel PCA, we are using Gaussian process latent variable, we are using different forms of clustering, etc. All the different techniques. And in the next phases, we will see how the different forms of decision trees, random forest, etc. works. I have unfortunately not been able to attend all the workshops. I'm not entirely sure if any of you taught through decision tree or random forest, but I'll do it in a bit of a hand waving structure without going into the detailed mathematics, just giving the hand waving argument and then showing what sort of a Python code will bring this into life. So basically, given the data, all you need to do is copy paste the code, I mean, that 4 or 5 line code that I give you, and that will do the random forest or the decision tree analysis for you. That's the approach that I will take. This one is drug repurposing, and we are so excited. MRSA, please don't ask me what the full form of that is, because I always make a mess. It's popularly called the step bacteria, and basically methicillin streptococcus something something, I have always forgotten it, but basically it comes up like a skin disease. It is not a skin disease, but it shows up on the skin. It is a bacterial infection which does not have an antibiotic for many reasons, but it doesn't at the moment. And what we have brought about, it was another PhD project with three students, one from Vietnam, one from Nigeria, and the other one from Poland, who independently and eventually combined, pulled up the socks together to assimilate the information which we are proposing as a combinatorial new MRSA antibiotic. And that's the one that I will end up this part with. Let's get started. So, what is drug repurposing is the question that I will get started with. And in the process, I will show you some of the very exciting things that we have done. I will show you some implications of how the whole mechanism works, because I remember in one of the talks that I attended in this data workshop, one of you, two of you actually, did talk about the challenge in translating letter sequence into number sequence. As an example, so if I have a DNA, so I have ATCGU. If I have an RNA, I have ATCG. If I have a protein, I have 20 A1 to A20 amino acids, right? Now, let's say I'm taking the simplistic example of ATCG. Now, if I am looking at ATCG as a sequence, so you have two A's, then maybe five T's, three C's, 25 G's, etc., defining a certain bacterium or a virus. Okay, so that's, or a certain RNA. I'm just trying to be a bit crude, but trying to explain it. But basically, the challenge is, given the sequence, so nowadays you even have full access to the COVID database. So that means a chain of this and there's different proteins. So question is, can you interpret the data set? This is the holy grail of bioinformatics, to find out what we call the active regions, popularly called the active regions, and we will see what we call them in the bioinformatics jargon in a second. But basically, which active regions are responsible for the virulence of that particular disease? That's exactly what we are after. Okay, and the first challenge towards that is you need to translate your letter sequence into a number sequence. You can say, I will stick to the letter sequence. You can stick to the letter sequence, but computer doesn't read letters, computer reads numbers. So you need to translate that to numbers. Now, why not ATCG, for example, becomes 1, 2, 3, and 4? Who stops you? Well, nobody stops you, but that will give you rubbish. Why does it give you rubbish? Because it does not conform to something called a propensity scales. So what is a propensity scale? Propensity scale is, now we're going back a bit into the domain of chemistry. I'll take a very simple example. So let's say we take you take a paracetamol and you drop it in a glass of water. The paracetamol dissolves in water, right? You take the same paracetamol and you drop it in a glass of alcohol. It dissolves in alcohol. Okay, fine. Now what you do is you take a vitamin capsule, vitamin E, for example, open the capsule, put it in a glass of water. It won't dissolve because it's basically oil. You put it in as properly charged alcohol, it will dissolve, or something else. Mostly in acetone, for example, it will dissolve. The point is, um, materials or different compositions, different and now coming into the more focal points, the DNAs, the RNAs, the proteins, they have different responses to the ambient infrastructure. So if the ambience is, for example, hydrophobic, they have a certain reaction. If it is hydrophilic, they have a different reaction, and that reaction is entirely the property of that particular protein. And hence, what people do is, and this was how I actually came into the domain of bioinformatics. When you measure what we call the propensity scale, so each such biochemical reaction is called a propensity scale, and it is measured in terms of the kilojoules. Basically, it's energy unit. And typically, each protein can be calibrated against 553 different such propensity scales. So imagine now try to translate that into the language of statistics. So imagine you have data for 10,000 proteins. Okay, so 10,000 proteins. Each of them are in three dimensions. Each such dimension has 553 different propensity scales. Can you imagine how complicated the structure then becomes? Right? So that's the sort of challenge that people deals with. And when somebody says, well, out of this 553 by 3 by 3 for the three dimensions, you pluck out those 2, 3, 5, whatever dominant and the most important variables. That is a real challenge, because once you can do that, you can put a finger on literally the point saying these five are responsible for this particular behavior. That thing is called feature mapping into functionality mapping. So that is the holy grail of bioinformatics. What we are trying to do here is we are trying to read it from the reverse of a mirror using drug repurposing. Reverse of a mirror means we are taking drugs which are market tested, and we have actually used drugs that are in the market, trial 1, trial 2, trial 3. That means the three failure drugs, but failed sort of for marginal reasons. So basically, what we did is you analyze these chains of all these different drugs and find out which protein chain from your drug side conforms best to your MRC site. So it essentially means that your pathogen has a chain, it's a protein. So a pathogen maps against another protein, which is your drug. Which drug gives you the best possible matching? Whichever does, it's your medicine. That's pretty much what we are using. So basically, we are looking at the known drugs with the side effects, with the failures, with the success, and we are trying to, with some luck, find if we can find a good drug candidate from the known drugs. Remember, these drugs I'm talking about are not just antibiotics, they're completely unconnected drugs. Some of them probably treating stomach ulcers, some probably treating your lung infection, etc. So those are dramatically different things. But then again, some chains might actually spark an interaction with some other chain that we are trying to decode. That's the challenge here. Okay, so this is how we will do it. We will use data mining for that. Okay, the challenge here is, so this is in itself a long talk. I won't go into all the details, but just to expedite. So basically, to make a drug, it takes somewhere between 18 to 25 years. And just a classic example of that is vaccine repurposing. The best possible example are the COVID vaccines. They were repurposed from the known vaccines or the known features, which is why we all got the COVID vaccines by within about 4 months from the time of their inception. That was the reason. So it's a completely different ball game altogether if you can repurpose. So classic examples, I will just give you some target examples. So basically, again, I will not spend much time on that. This is a very popular example. The Viagra as a drug was and still is a very, very powerful drug in treating palpitations, heart palpitations. Obviously, we know it has a completely different usage. Now, how come this usage became known in the first place? This is not the unique example. So there are lots of other examples that I'm tabulating here, and it's a very small list. This is the next most important one, aspirin. Aspirin was typically, in the first place, given as an analgesic for minor pains, okay, just to reduce fevers, but what your medical doctor will call antipyretic or anti-inflammatory. What is it most used of nowadays? For two things. One is colorectal cancer and as blood thinner for the cardiac patients. We all know this, right? Many of you probably might even have to taken it at least to your parents or somebody in your family. So aspirin is now being used for a completely different purpose than what it was initially envisaged. Now, does that mean it was a structured deduction? The answer is no, it was not a structured deduction. It was a deduction by accident. It just happened that people found that it works. And then people, well, did more chemical analysis of that and found why it works. But in the first place, that knowledge was not a structured knowledge. So, what we are trying to do, what everybody is trying to do in the world of computerized drug repurposing, machine learned drug repurposing, is basically to put not the cart before the horse, the other way around, basically to put a connection, a logical trajectory between the different drugs and their formulations. Okay, so here are some other examples. And in the list that you will see, old means the original reason for which this drug was devised in the first place, and new means the popular applications. Okay, something that was devised for cancer is now a more popular medication for gout, and so on and so forth. And these are the manufacturers, so these are the popular names. The rightmost column are the popular, the manufacturing names. Okay, so the journey would be like this. So you get the structures, okay, and then you basically do and analyze the molecular biology and the protein chemistry. Now, how the hell would you do this? We will come to that in a second. This is done by something called talking. So these are normally, or at least traditionally, used to be very expensive, something to be paid for software that will basically analyze the entire three-dimensional biochemistry of the molecule, track all these 553 or so propensity scales, and give you some information. The tragedy with that approach is each algorithm was lame in its own context, essentially meaning it's like a prism. So imagine if I'm looking at the prism from the left, probably I see it glow red. From the right, somebody sees it glow blue, somebody looking at it from the top sees it yellow. The prism is neither red nor blue nor yellow. The prism is still colorless white. So essentially meaning you need to combine all this different information to get the white infrastructure, and none of the market, however expensive software it might be, uh, um, um, docking infrastructures was allowing it to do that. And for a very long time, I would say going until the about 2015-ish, the entire chemical world, there was a lot of wrangling and sort of infighting in between them, each claiming their software to be the better than the other one. What we have tried to show here is, hopefully we have, is there is nothing called a better software. You just need to do something called consensus scoring. That means you combine infrastructures from all these different things, the red, blue, green lights, to get your white, which is your target, which none of the independent architectures are capable of. And we will show it with proof. And eventually that information will lead us to this new mRSA antibiotic drug. First, let me show you something where the journey started. And this I will show you um, by running the code in front of you, literally. So just to give you an idea of how the whole thing sort of looks like. So this is a very simple example. So imagine I'm showing you some data, okay? Just look at how the data looks like. So these RBP, BBP, MUP, etc. These are different RNA chains. Okay, so the first one spans this long. Second one is about that long, etc., etc. Okay, this is just to give you a visual of how the input data looks like. 2 points: randomized chains with hidden instructions. Point one, and the point two is they're all in letters. So the first challenge is translating the letters into numbers. And this is something for which this is a paper just to be submitted. The propensity scales that we have used here are the following. Numbers for A, T, U, C, and G, and these numbers are basically the chemical units. Now, please remember, I've used only two of the propensity scales, 553 possible propensity scales. One is the chloroform water partition one, and the other is the free energy of salvation. There are lots of others, as I just mentioned. But the infrastructure can automatically adapt to any number of such input scales, propensity scales, that you want to incorporate, induct in the scenario. Okay? Now, this is what it is. And that's how, just it's nothing to do, but this is how our Python code actually looks like. We will be making it proprietary. This is just a glimpse of what is in store, but basically it can handle, and this is a GUI version that we will make market available. For those of you who have used it, you will know it, but those of you who haven't, TK inter is basically the GUI generator using Python. It's slightly old fashioned. I think the new one is called PQ Lite, I think. But I haven't actually trial tested the new one. And the TK inter one still works, slightly slower than the terminal version, and I will show you how the terminal version actually works in translating the thing. So what exactly am I trying to do? Sorry, go back. These are the scales. This is the data. What I want to do is I want to take information from the scales. I want to take the mean of the scales. I want to take the reflections of the scales. I want to take a running average of the scales, etc. Each in its own way, generating a different sequence that I will show you how it looks like. And the sequence eventually will all be ensemble average to generate my information. What we are saying is we do not know which sequence is the more logical one. So we'll take all of them and we will sort of gel them together to extract a standardized information that assimilates information from all of them, not without any bias for any particular one. Just to show you how the whole mechanism actually looks like. So I'm just literally running it on a terminal. And just to show you, there is no output at the moment. Okay, I'll show you what the output looks like, but there is no output. So first of all, I am generating some outputs. Okay. Okay, I'll use all the data files. All the data files means all these input long chains that I've just shown you. There are 4 of them. So I have not changed the periodicity. I've taken all of them, have not flipped them. And if I put a flag before I run it, I can do all of that. In the GUI version, you can simply click and do all of that. It's pretty fast. It will do the job in a few more seconds. Let's just wait. Okay, the results are there. I showed you there was nothing before, and now you have things here. Okay, so in the different forms that I have averaged them, I have only used the first propensity scale, this chloroform water partition. I've only used the water, the free energy. Let's just look at the average one. Just opening it up, do you see that the letters have now been translated into numbers? And I've also calculated the degree of randomness of the data, which is measured by something called a Lyapunov exponent. I will not go into the details of what that is. Anybody associated with chaos and nonlinear dynamics will know that. But it's basically a measure which is measuring the maximum entropy of the distribution of data points. Okay, so just to connect, maximum entropy means a stable equilibrium, minimum entropy means chaos. Okay, so the data is moderately chaotic, as you can see. Now, just bear in mind, if you can, just keep in mind this first one, 0.01428, okay, 0.012824. That's the reason I'm saying that, because I will now rerun this with a flag. I will just change it with, let's see. These are the different flags that we can attach. I'll just flip read it, just flip it. So it is generating new data sets now. Everything remains the same. The flip has become true if you can look at that. Periodicity is still not affected. The mirror reflection is still not affected. That's called complement. And it is generating a new set of data. I will go back to the same average data set and I will try and see what the new number looks to be now. And you will find that the numbers are numerically different. So I think I probably open the first one, averaged. Do you see that you have a different score now? So look at all these different numbers. So they are turning out different score lines. Okay. And the score lines will vary. The score lines will change, obviously, depending on the sequence that you have wanted to convert. So this is BBP, one of the sequences. This is another one. These are all the different RNAs that we wanted to compute. Instead of RNAs, we can do proteins. You can do anything. Okay, so this is a very important first step in the data modeling process where we are translating the data into numbers. Itself, it was a big challenge. And this the spy skills software is actually now available through GitHub. So we have released it for everybody's usage. Okay, so like what I said, this is how it looked like, the chain. And if you plotted them, the output will look like this. The different colors are representations of the different forms of averaging, sometimes flipped, sometimes with a complement, sometimes running average in different step sizes, 5, 7, 9, etc. And all the different plots are shown. Please note, all the pictures, they look quantitatively different, but they're all coming from the same sequence. So when you do your statistical analysis, machine learning, data modeling, whatever you do, remember, if I am taking, for example, the red one here and somebody else is taking the green one, the results will be different, right? And neither of them is individually right. So what we need to do is we need to take all of them together and combine that information, standardize it, and extract the mean. Mean means not the arithmetic mean. Extract the standardized information set and call it your prediction, and then map, this is the training still, map the training outcome against your prediction to see if it makes sense. This is available here. Okay, so this is the whole journey now. So you start by docking the actual molecule. So what does docking give you? Docking gives you all these data for the different propensity scales. Okay, so that's what the docking will give you. Each docking infrastructure will come out with its different score, just like what I have shown you. And we will say we will not bias ourselves with any particular infrastructure. We'll take all of them, and meaning a certain number of them, and then we will ensemble average. BLAST is a very popular docking architecture, one of the most popular ones. And what it does is basically it takes that information and translates that into a network, basically. But this is, and these are the different chemistry descriptions, but basically what it does is it unravels the protein into more accessible um, tree-like structures, if you like. So that's what it does. So this is inbuilt. We have got nothing to do with that. BLAST is freely available. You can download, you can run it yourself. And it generates, you can get all these information from something called the Protein Data Bank. This is free, open sourced, open access for anybody who wants to. Okay, so now we have used all these different potential MRSA targets from the Protein Data Bank. These are the names, identifiers rather. And we used decoys. Decoys means the experimental ones, and so these are like the targets, and only one active ligand, which is what you want to map against the targets. Okay, so just to show you some results. And the important point is we use 10 different docking programs. Now, let's stop a second here and ask ourselves once again the question. You can ask me, you have said that there are many different docking programs and they're freely available. Some are expensive, but a lot others are freely available. Which one should I use? Okay, I told you that we used to combine information from all of them. Now you would say all, but I mean, there are hundreds of them, and the results that I'm showing you are the results coming from supercomputers. The supercomputer in Riken in Japan. So all of this is possible nowadays because we have supercomputers, because with supercomputers they take weeks to run and churn out the first set of data. So how many can you possibly do? Well, the answer to that is you don't need to do a lot, and that's what is one of the cream outcomes of this research. You can focus yourself on a randomly chosen small 5 to 6 of them, and then you will hit the saturation limit of accuracy. I'll show you in a second. Here, ADFR, never mind what it means, for the same set of targets is returning you scores like minus 7.7, minus 8, etc. Okay, now I'm using doc. Look, what was minus 7.7 with ADFR? With doc, it's a completely different number, completely non-standardized. I'm taking another one, GemDoc, another set of numbers. So each one of them are returning different numbers against the same propensity scales. And the challenge is to standardize them. So we used some nonlinear statistical algorithms. So we used pretty much these, where A and B are basically sometimes the mean, sometimes the median, sometimes the mean max normalization, etc., etc. And we tried to see which, if any, would actually consistently enable us to combine a small finite number of consensus scores and score higher than any individual talking program. This is the question of validation and reliability. Okay, so this is basically the combinatoric, the combined outcome coming from all the different scores, renormalized and averaged across all the different propensity scales that we had access to. And this is how you rank them. When you rank them, look at what's happening for some of them. So, for example, the ADFR is scoring very high, comparable with the doc, which is sort of the industry standard go-to program. And we are saying there is nothing called industry standard. It's a myth. It can be counteracted. So if I change this to something else, this is the indicative plot. It is actually showing us that the linear and all the odd ordered combinations, odd order would mean SI cubed times an XI, which are the weight factors. So this red line in each of the plots that you see are the scores from the best industry standard docking program. And the blue patch to the left, the size of the blue patch tells you how good the combinatoric is. Already you can see that the area of the blue patch is much larger than the area of this delta function like structure, like this red delta function. Okay, so this is telling you that combinatoric mechanism is better than an individual score. This is sort of the summary of this gist. And we tried to combine it against many linear and nonlinear combinations, and you will see the size eventually reducing. So for the higher order correlators, the contributions are minimal. The lower order correlators are higher in number. The odd orders contribute. The even orders do not contribute. So essentially, it means there's some level of symmetry inside the system. So you have what you call an odd symmetry or parity in the system for the set of data that we are talking about. But we are not going into those mathematics here. We're simply taking the data and we have gone up to the basic level. And this is an important finding. This finding tells you that it is not necessary that you have to use hundreds and hundreds of talking programs to get the desired level of accuracy. Up about 7 randomly chosen docking program is good enough to give you the desired level of accuracy, beyond which it really doesn't matter. Okay, and this is measured using two different accuracy definition. One is the area of that blue patch plotted against the number of the docking programs, and this is the competitive ranks. Those box plots that I showed you plotted again, it shows you the box plot is even more illuminating. It shows you around about 5 docking programs is good enough to give you a very high level of accuracy. And our docking is better. This consensus scoring, as we have named, is better than any individual docking scores anywhere. Now, the next step, what we wanted to do was we wanted to benchmark that statistical finding against unsupervised k-means and then a dendrogram clustering. Okay. So what we found is, after that long journey was over, we found out that these three, something called a PPT2, prime protein target. So this is one of the possible drug candidates. Prime protein target 14 and prime protein target 27. And these, when suitably combined, suitably means with weight factors. Here we have given the weight factors as well. When combined, gives us this particular information. This is the new potential MRSA antibiotic. It should combine 63% of PPT2, 19% of 14, 18% of 27. And we have also given options for alternative candidates like PPT14 with PPT27, 15 with 22. Now you can ask me what would someone do with all this information? Well, someone will now take this to the wet lab and actually generate the new drugs and start treating, well, to start with animals and see how they actually perform, and then taking it to the usual drug validation program into the market. So potentially we have, and of course there's a stage in between that, we also need to do some molecular dynamic simulation to find out whether these drugs are actually time stabilized. So the important point is, this is another very important and powerful application of machine learning, which can actually show how to apply these techniques in real world regimen. Again, I will stop for a few seconds. Any question? I admit that it is not exactly, I mean, in line with the sort of Python training programs that you have enjoyed so far. But what I'm trying to, or rather, I'm hoping is those were very good grinding for all of us to now venture into something to apply all those knowledge into real world platforms and see what we can do out of that. So, this is more or less my target.
Regarding
Okay?
the accuracy slides, I mean, I observed that accuracy becomes constant in some stages, right? Accuracy
Here.
becomes, yeah, this one. Depending on the number of docking programs. If you increase number of docking programs, accuracy becomes still constant, right?
Yeah.
What is the reason?
Oh, okay. This is a very important point, Shweta. Again, this is one of the, I would say, one of the two major success stories of this study. See, up until when we had a big bit of a problem in actually trying to get the first paper published because we were fighting against the community, which is the community of um, chemists, inorganic chemists, and supported by bioinformatics people. They always, for all these last about 25 to 30 years, they have consistently done docking, each belonging to a certain docking school. So basically, docking school 1 would say mine is better than docking school 2, and all these were proprietary expensive software. Now, like what is said at the start, each docking, however efficient it might be, just because of the limitation in the chemical way the algorithmic structure works, they cannot process the entire three-dimensional structure of the molecule. So they will at best can give you, let's say, like 10%, 15%, even 25% of the whole molecule. They cannot look beyond that. Okay, so now it depends on which 25% you are looking at. You might be looking at the left 25%, somebody else might be looking at the right 35%. The left 125, whether the left 25% is more important than the right 35%, we don't know. Nobody knows. But you need to have all this information assimilated to talk about the entire molecule. So our way basically is saying we are randomly choosing the docking platforms, the free ones, actually the open source ones, and we are combining information from all these docking platforms without actually believing that any one of them is good enough. We are saying that the sum total of them, do they score higher than any individual docking platform standard that we are used to? And the answer is consistently yes. And that number doesn't have to be, because it could have been the case that somebody with super access to computational platforms, they may say, I have access to a lot of computation time, so I can do docking over 50 docking infrastructures, and they're extremely time consuming. Okay, so and I would have to say that I can at most do 5 in 2 years. That's how time consuming these are. So they will be in the game, but that is not like that. So what we are showing here is 5 to 6 docking infrastructural information is more than sufficient to lead us eventually to the MRSA antibiotic, or for that purpose, any other medication that we are targeting. So basically, it's saying here about 5 different programs have combined to give you that white color of the prism. That means the entire three-dimensional structure of the actual studied molecule.
Okay.
Make sense? Okay.
Yeah, it's okay.
So now we are going to the last bit. So this is the team that we were working on, and these are the list of publications, and yeah. So this is the last bit. This would be personalized oncology, so that means cancer treatment, zone-specific radiotherapy. Let me try to propose the problem. Again, I have sort of collated information from an independent, what I think would be an independent talk, and I will not do it that way. I'll just give you the outline, and then I will stop for questions. So the outline is very simple. We all know, and this is something that I think I mentioned during one of the presentations. The outline is the following: that imagine that somebody has a tumor, cancerous or not is a different question, and the treatment suggested, typically cancerous tumor, treatment suggested is a combination of chemo and radiotherapy. So when that particular tumor is exposed to the ray, which is a very heavy radiation, what happens is it doesn't only kill the cancerous cells, it also kills a lot of benign cells. I mean, it also kills a lot of good cells along with the bad cells. And often, the side effect of killing the good cells is such that the patient dies or otherwise has something called a paralytic reaction against this particular form of medication. And instead of that medication doing any good, very often it turns out even worse. And we all know this. So lots of efforts internationally are going in the direction of identifying what possible mechanisms could one design so that the array, when implemented, zooms exactly at the tumorous spot, at the benign spot, and nowhere else. Okay, so this is one of those approaches, and our approach is basically using nanoparticle based drug diffusion. Why nanoparticle? Nano because it's nano sized and hence very small, and they are completely non-interactive to the bloodstream. They do not interact. There is no good, bad, any form of effect when you're releasing them on in the bloodstream, coated with the basic medication. So what they do is they flow with the blood and they go and settle on the cancerous spots. Now, you could actually stop me here and say, well, how do they know what are the cancerous spots? And this is a very interesting thing. And this is what explains the strategy that we have devised. I'll come to that in a second. But let me first give you an idea of what are the different forms of standard medication, so the data that I will show you. And I will go into a bit more of data modeling here. The data that I'm showing you are, I mean, we are talking about here, that means the mice have been treated using a couple of different medicinal forms. Saline water is one of the most popular treatment for them. It actually does release them to a certain extent of the tumor, not entirely, but to a certain extent. And then people have treated them with many different forms of some that we have used, something called magnetic nanoparticles. MNP stands for magnetic nanoparticles. FDG is fluorodeoxyglucose, and the last part, I'll come to that in a second. FDG basically means it's a glucose-coated magnetic nanoparticle. Okay. Now, why we coat that with glucose? And this is the beauty of this entire approach. I'm not claiming it is mine. It's actually the experimentalists who envisaged and implemented that. So what they did was they found out that the cancerous cells are very hungry all the time. So that means they always want to eat a lot. And that's why we die, actually. So they basically eat out the good cells. Now, eating means what? Eating means they're very glucose prone. So if you dangle a glucose in front of them, they will go and gobble it up. And that's what they actually used. So they released glucose-coated magnetic nanoparticles, which automatically were gobbled up by the cancerous cells. So they basically came and settled on the cancerous cells, diffusing otherwise throughout the bloodstream without any particular implication for any other cell. So they came and settled definitely on the cancerous cells. And the next bit is they're coated with not just glucose, but with iron oxide. And I'll come to that in a second. Why iron oxide? Because iron oxide basically increases the what we call the surface exposure. So that means the iron oxides give them access to them, means they have access to the maximum surface area, and hence the volume of medication that can drift into the tumor is higher. Second, they are paramagnetic, super paramagnetic. Actually, they have a different name. They're called spions, super paramagnetic. What does it do? Well, it's exactly like what you do with a magnet. What does a magnet do? So just imagine that on a table you have a lot of normal dust, and here's some iron filings. Now, if you pull a simple bar magnet over the top of the table, the dust will lay where they are, but the iron filings will jump up and come and sort of get attached to the bar magnet, right? We have done this experiment in the past. It's pretty much like that. So basically, if you coat them with this iron oxide, basically they gravitate towards the magnetic exposure. That's the other trick that we are using. So it's a combination of iron oxide which makes them target specific, and coated with glucose, which makes them tumor specific. So it's personalized both in terms of the medication and also in terms of the patient. Okay, so and saline is not just normal saline, it's plasma activated saline. Now I have to put my hands up there. I'm not entirely sure why plasma activated saline is stronger than saline itself, but I've been told that's what it is, so I'll go by that. Okay, so there are different names for that. I will not go into this because there's something called a Warburg effect, but never mind what it is. But basically, the main key points here are it's non-toxic, it's target specific, it's with maximum surface exposure, and it this being iron coated, they react against a magnetic external um, uh, force, right? So this is the real data. So the first one, so we had access to, and this is another interesting study. This Land et al. 5-day study was the one that was conducted in one of our collaborators' lab. All the other data that I'm showing you here are from the literature. And if you'd ask me, how did you get access to the literature? So basically, we used a MATLAB inbuilt infrastructure called Granite. You have something similar in Mathematica as well. So basically, there are other alternatives as well. So what you can do is you can generate synthetic data by extracting data from the published plots. So basically, these are not exactly the real data, but they're proportional data, right? So the real data, instead of being 1.1, 2, maybe your proportional data is 20, 40. It's the same thing in terms of the proportional level. So that's what we have extracted here. That's what we call synthetic data from the published literature. The published literature that we focused on, these are very celebrated studies. One was this one called Key et al., and the other one that I will show you later is called Howe et al. So Key et al. Had access to 30 days of data. Now, what we did, and this was just think of the challenge. Land et al. Experiments were being done in Aston University in the UK Midlands. Certain type of climate, a certain type of lab structure. Key et al. Study was being done in, if I remember correctly, in Cambridge in the United States, right? So some study was being done in America, some in the UK in completely different lab conditions, and we're trying to match them together and compare, and we're trying to decide on a treatment regime that can actually span across both, because both are treating mice, both are using the same form of medication, and we're trying to make a bridge in between these. So what we did, it was an adventurous first step. So we used this 5 days of data for training the data. Okay, and then interestingly, for the remaining 25 days of the Key et al. Data, we used it for prediction. It's a very risky strategy because normally people do at best 80% training, 20% validation. We have done basically 1/6 training, 5/6 validation here. Let's look at how it works across a whole different set of machine learning and deep learning algorithms, and I will, in a hand waving gesture, explain how it matters. So first of all, what you see plotted are the size of the tumor measured in volume against the number of days. And this is, so first of all, when they're left untreated, this is this purple patch that you see grows. If left untreated, they keep growing. They sort of saturate beyond a certain point. You will say, why does it saturate? It saturates because the cell is about to collapse. It's about to metastasize. So at that point, there's very little ingredient from the cell to draw their ingredients from, and hence it saturates to a certain extent. With saline treatment, it is the red one. So it initially doesn't work and then eventually works to a certain extent, and it does a good job with the 5 days. And with the magnetic nanoparticles, which is the green line, they start working straight away. But apparently, in a 5 days time span, they're not as good as saline itself. So, of course, we would ask the question, why even bother then? Okay, we will think about that later. But this magnetic nanoparticles coated with glucose is the one, as you can clearly see, is the blue line. It is doing a fantastic job. It's actually completely suppressing, destroying the cancer straight away. Okay. Now let's see what happens with the other results. The other results are actually showing the same thing. We have stored them and we have plotted them volume against time. Let's see. I will hop skip all of that. So basically, like what I said, the statistical data were collected under different lab conditions, in different places, under different experimental ambience, and so on and so forth. So basically, they're not standardized. So statistically, there are many different forms of standardization, and we have used 6 different standardization forms. So just recall the z-score. This is the z-score, your data minus the mean divided by the standard deviation. Mean max means data minus mean divided by the range. Box Cox is basically a blocked structure, and this is what it does. And there's a logarithmic amplitude adjustment. That is not something that we have done a lot. It just is sort of historical anecdote. Now, look what's happening. The red color is clearly showing, is meant to show that this is the training regime. The blue one is the one that is the prediction one. So basically what we have done here is we have superposed the training done from the LANDS data, the 5-day data that we have genuinely access to, which is the red cross, and we have pulled the 2 data regimes on top of each other. And do you see that it's giving us sort of a very good normalization? So the normalization mechanism works, and we have done it across a whole range of different normalization. So we could now actually combine the 2 data through the normalization, which is the purpose of doing it. Okay. Now we have used 4 different forms of machine learning process, and I will give you a hand-waving argument of how and what these are. Decision tree. Imagine you are looking at the branch of a tree. Okay, so just think of the main stem of the tree, which is a solid straight line-ish sort of a structure. So you are going from the bottom to the top, or from the top to the bottom, or if you're looking at a branch, you are going from one node to the end of that particular node. That's the decision tree. A random forest means when the tree has a lot of different branches, so you're tracking the movement of the branches. Okay, now naturally, a random forest is the collection of a lot of these different branches. That means a lot of these decision trees. So decision tree is sort of the starting one. Random forest in general is the correction on top of that. Multilinear regression, it's sort of a borderline between statistical and machine learning. What it does is it does fitting based on maximum likelihood estimation, MLE, instead of least square fitting, which is much better in such circumstances. Okay, so it's and it's linear. So multilinear regression means, imagine you have n number of variables defining a certain process, and you are trying to project your outcome on all these n different variables, much like what I explained to you when I was explaining the PCA infrastructure. So basically, it's still linear, and it is still a very popular methodology that people try and use. One reason for that is it is sort of borderline, if not exactly probabilistic. And then the best one, it's like an adaptive neural network. It is how a brain neuron functions, and that's what the origin of the name is. A neuron is like a pulse, excitable pulse. So it switches on. There's a start-stop process, 0 and 1. 1 means it's activated, 0 means it's inactive. And once it's switched on, it basically connects with the different branches. So basically, it is a way like it's a multi-activated random forest, brutally. That's the way you can visualize it as. So if you want to use it in your random in your Python code, all you need to do is you use your sklearn and you just import your decision tree regression. Okay, instead of a decision tree, and I will show you again. If it is a random forest, everything else remains the same. Decision tree regression becomes a random forest regressor. Do you see that it's exactly the same thing? Okay, this description you can do without random state 42. Random state 42 is the Python trick which essentially is used to minimize the unwanted noise in the data. What it basically does, it throws out the fringe fluctuations from your data. In most cases, it is a better thing to do. But of course, when you do that, you also need to do without the random state 42 and check if it is a better, if it is for your test set, if it is giving you a better function. Normally, this gives a better function because streamlined data should not have fluctuations. So fluctuations are numerical artifacts that should be read off. And this is what is inbuilt within the Python architecture. Okay. So the reason I'm trying to hammer this a few times is you are repeating the same Python code. You literally copy paste. So DT for the model is basically just calling in the decision tree regressor here, whereas for this one, it's a random forest regressor. Okay, and you are basically estimating it across 100 different branches. That's what the random forest is doing. So 100 different decision trees. Multilinear regression does pretty much the same thing. Everything remains the same, only now you're importing linear regression. Okay, just to save time, I have not just copy pasted it on Colab or on a Jupyter Notebook, which I actually had open as well. So it's pretty much doing the same thing, and all it's doing is it's fitting y versus x. So y is your projection, x is your input data. Okay, and I'll skip jump all of that. I'll show you the results now. Okay, look at what's happening here. The first one is using min-max standardization. The second one is simply mean. The third one is again the same thing. So the first one is doing a min-max standardization of the data. So look carefully what's going on. The red crosses here for the first 5 days are the land et al. Data. The green crosses are the land extrapolated data, if you extrapolated the land data. And the real data that you see that are not exactly, at least between 5 to 20, they are quite different to the land extrapolation, are the key data from the different labs in the United States. In other words, if you were to simply pull the data points like what you would normally do in a simple data fit, simple extrapolation, it will fall blank, miserably short of reality. It will be a bad approximation, bad realistic, and it doesn't matter which form of standardization you have used. Both forms of standardization are not capable of capturing these fluctuations. Okay, now let's see what happens with our model training. Look at the decision tree outcome. Again, the blue triangles at the start between 0 to 5, we are starting from the training part of that. So we have trained for the first 5 days both of the key and the land et al. Data, and then we extrapolated that data. So the predictions are these solid blue lines that you see here. The lines are actually pretty consistently growing through. The insets are actually giving individual matchings between land and between key. I've changed the model here, the random forest. Okay, this is the one, bottom one is MLR, the one after that is adaptive neural network. I think even from simple visual things, the disagreement that you see, well, the decision, the MLR was not doing a good job at all, and it was, you see the mismatch at between 0 and 5. It was not expected to do a good job because it's not a probabilistic method. Decision tree, random forest are fair, not terrible, but the ANN is doing an excellent prediction of the fact, and we will take it one step further. So now we have changed the data set, and now you see when the data set changes, the ANN still maintains its predictive power much better than the other ones. So we have just training the first 5 days of the data consistently able to predict the remaining 25 days of the key et al. Data and the remaining 11 days of the Gao et al. Data. So this is now the third data set in the fray. Okay, so adaptive neural network is very consistent. It returns the highest R score, almost 1, and the lowest RMSE score, which is about 4. Okay, and these are the comparative performances from the different machine and deep learning protocols. So clearly, adaptive neural network is the best performer of all these. And now we have used a different set of experiments. We have used this passive, this activated saline. So basically, not just normal saline, there's a plasma activated saline, and hence they are supposed to be more powerful in terms of treating the cancer. So again, what we see is ANN gives a very consistent quality of prediction. Okay, combining these two and using a logistic growth fit, what we have now done is a very key important prediction, which is we are predicting and precisely comparing how long each form of treatment, saline, MNP, and MNP FDG, will need to completely eradicate the cancer. And here is the result. I'll show you the results here. So complete remission with MNP FDG is 13.6 days. Hypoxia activated products. Hypoxia basically is a real drug regimen. The same mice, when treated to that drug regimen, please bear in mind, these are very expensive drugs as well with a lot of side effects, is 14 days, which is comparable to MNPFDG, which is very cheap. Exogenous epidermal growth 20, 16, plasma activated saline, the more popular form is 28 days. So the prediction is MNPFDG outscores all the other forms of treatment. And our suggestion is this is the right time for it to be now cultivated within the human domain and human implementations. So the key findings are MNPFDG is superior, AI is pretty much the leading light in finding all these different tricks because we have the protocols to match data against different algorithms and we can try and find what is best suited for that particular domain. I have done other studies, there are other results, but just I think I should stop right here. So this is the team we are working, and there are multiple papers published, a lot more to be published, and we are working hard on these.
Now the question session. Audience, please ask questions if you have. Any
I'm
questions?
sure I managed to bore everybody.
No, not really. Anybody, please ask any.
Hello.
Yes.
Yeah,
Yeah, excellent talk. Thank you for this wonderful session. We really enjoyed. It's not a question, it's just um, curiosity. So, regarding the drug repurposing project that you have been working on, so I guess you all have worked only on the docking bit. So, is there any further studies or thought about integrating the multiomics data, sort of?
the honest truth to that is, I will tell you, it's a very honest question. I'll give an honest answer. The honest answer is, so we got this Vietnam government funding to do this study. So this is how it all started. So the student came, did
Okay.
a PhD, and went
Mm-hmm.
and joined one of the top universities in his country. So did the other two. Now, well, not all of them. So did one of the other two. Now, the problem is, after that, we did some sort of follow up studies in the sense of paper publications, but we haven't actually taken it to the
Mm-hmm.
next level, like what you have just mentioned. So, and again, it is not limited to MRSA. I mean, the same protocol, there's no reason that we can't replicate the application to some completely different domain. So the answer is no, we haven't done it. And I'm very interested if there's an interest from your side, somebody else, we can certainly discuss about that.
Yes, yes. Yeah, I mean, I had done a project on the drug repurposing, but that was mainly on the bit of cancer line, and but that was heavily on the genomics side to it.
Okay.
But
But that's a very interesting direction. I think I would love to go into that. So combining the two regimes, actually, the statistical and
yes,
the genomic one.
yes, but I guess with the sort of big data and all the data that are available, so it's not only restricted to genomics, I mean proteomics and also epigenetics. So combining and also taking into consideration that we have a lot of image data.
Yeah,
So yeah, so that's
I that's exactly what we had to do a lot, and we are still doing this. We will keep doing that with cancer. See, the truth is,
yes.
if you are doing your experiment, if you have got a
Mhm.
lot of funding, well,
Yeah,
for whatever
yeah,
reason,
that's
you won't give me your data, right?
yes.
So nobody
It's
does that.
I think the biggest challenge is with obtaining the data and all the level data from one single source. I think that's the biggest challenge.
Europe, there is another big challenge, equally important, perhaps even more so. The issue of IP, the
I
ethics.
Yeah,
Ethics. So
ethics. Yeah, yeah.
anything related to any form of animals and human,
Mhm.
it's, I can tell you
I
the
mean, it was a
fun
big
line,
challenge. Yeah, in
it is an
Australia.
impossible task now because of all
Yeah.
these different bodies and all these different
Mhm.
regulations. In the
Mhm.
US, it takes at least 3 years for the data to be released after all these,
Yes.
assuming everything goes fine. In the
Mhm.
UK, it's at least 2 years.
Mhm.
2 years is a very long time. What would you do for these 2 years without doing anything? I mean, how would you pay your student or your postdoc? So
Yeah.
what we have been doing is we are relying on the published literature, so people who have actually undergone all of these and eventually published their experimental data. So we are extracting data from the published literature, which is legal, and then we are repurposing that for our
Yeah, I mean,
studies.
for us, we have to heavily depend on the already available data sets. So,
No, these are not even data sets. They're not releasing the data. All
okay.
we have are the published papers and the plots in the
And
published papers.
from
What else?
there, okay, yeah, yeah,
From the
okay.
plots, I can extract the data.
Mm-hmm.
That's what we have been doing in the cancer one.
Okay. All
Any other
right.
questions?
Yeah, that's a area we would be, yeah, would like to connect. We can,
Sure, get in touch.
yeah, yes.
Very welcome.
Thank you.
Any other questions or comments, please? If there is no other comments, then I have a comment. Previously, I was confused about why did you use four different types of machine learning techniques, but later you clarified this. Why did you use this? So I don't have any question. The second comment is that I wanted to see your background of your room, but you unfortunately blocked with the virtual background. Okay, so
I'll show it to you at a different day.
okay, okay. So I am really thrilled to thank Amit for his absolutely stellar talk on machine learning today. As a convener, it was a pleasure to watch the audience captivated by his deep knowledge and practical insights. Amit brought real world examples to life, making the complex simple and proving why he is a leader in this field. Sure, thank you, Amit, for making this workshop an unforgettable experience. Thank you very much.
Thank you very much for inviting me and
So,
hearing me patiently.
okay, so we shall meet tomorrow again, perhaps 30 minutes earlier because there will be a closing session and we want to stop it by 9 o'clock. Okay, so we will notify when we will start. So, thank you once again and good night, everyone.
Thank you. Thank you.